Good morning. Back in 1958, something interesting and momentous happened. A TI engineer named Jack Kilby invented this thing. And what is this thing? This was the first integrated circuit, which took transistors, which had hitherto been single standalone things, and put them together on one piece of silicon called a chip. A few years later, Texas Instruments and other companies began to develop large-scale integrated circuits combining many transistors on a chip. And a guy named Gordon Moore, who was the CEO of Intel, one of the early founders, came up with an interesting observation. He noted that by reducing the size and increasing the density, you could continue to fit more and more transistor equivalents on one single chip. In fact, he projected that the number of transistor equivalents that Intel could fit on a chip would roughly double every 18 months to 2 years, with its cost halving during that period. That's a hell of a projection for something back in 1965 when he first made that prediction. And the interesting thing was they hadn't gotten a whole lot of transistors together on a single chip at that point. So when he made that projection, starting from the beginning of the invention of integrated circuits, he was already behind the curve. But you know what? Let's take a look at what has happened in the years since Gordon Moore made that projection. By 1967, he was projecting that they should be able to have 90 or 100 transistor equivalents on a chip, but they still hadn't done even one of them yet. By 1970, his projections, if he was going to be accurate, was said you should have 500 of these transistors on a chip, but they still hadn't happened yet. Wait a minute. By the time you got to 1970, Intel had the 404, a CPU, central processing unit, that had thousands. And all of a sudden, they were actually matching the projections that he had. And so this is a chart showing that as time goes by, what his projections would have meant. This idea of doubling every 18 months to 2 years, the number of transistor equivalents that Intel could fit on a chip. And you can see at times it looks like they could never keep up with that, but then technology comes into place, and all of a sudden, with the 8086, which ran a whole lot of computers during that time frame, you could stay ahead of Moore's law, and they were packing even more transistors onto this chip than Gordon Moore had predicted. But the pace of prediction kept increasing because you were doubling every 18 months. And by the mid-1980s, Moore's law, as it came to be known, was projecting that you could fit hundreds of thousands of transistor equivalents on a chip. And guess what? Intel was doing that. And Motorola was doing that. And Acorn was doing that. And all of a sudden, it looked like maybe this was actually a real law, not just an observation. And so by the late 1980s, 1990, it seemed really difficult to believe that they could actually continue to develop chips which had as many transistors as the projections of Moore's law would have you believe. 1 million? 2 million chips by 1991? Oh, okay, looks like we finally outstripped it, right? And they can't catch up. Yeah, but guess what? In 1993, you now have the Pentium came out, which revolutionized desktop computing with 3 million transistor equivalents on a single chip. But still, time marches on. Moore's law's projections march on, doubling every 18 months to 2 years. By the late 1990s, his projections are saying, hello, you should have over 25 million transistor equivalents on a single chip. And while they didn't quite get there by 2000, take a look at what's happening. But you had 42 million there in 2000. You had 60 million as it keeps going by 2001. And then by the time you get to 2002, you have the first titanium chip comes out, and this is now beating Moore's law. You now have 410 million transistor equivalents on one single integrated circuit. And just when you think it couldn't go any higher than that, the inexorability of Moore's law continues. You now have, by 2006, the dual-core Itanium 2 has got 1,700,000,000 transistor equivalents on a chip. Whoa, look at what Take a look at what Moore's law is projecting right there. Moore's law is projecting that you're now about going to have, more than 2 billion on a chip. And guess what? You continue to have between NVIDIA now creating graphics chips and Intel with their Xeon chips. You're actually doing more than that. You're now up to 7 billion transistors on a chip. And Moore's law inexorably keeps on going, projecting you should have 6 billion, 7 billion, 8 billion. And by 2015, 2016, you now have 10 billion transistor equivalents on a chip. You're now talking with the NVIDIA Pascal, you're talking 18 billion. You get to 2018, Moore's law is projecting that you should have close to 25 billion transistor equivalents on a chip. Now that's where this wonderful graphic animation ends. But you think it stopped there? No, it didn't. As a matter of fact, I don't know if any of you last month watched the release of Apple's new M3 chip, but you want to take a guess, if you don't already know, how many transistors equivalents Apple managed to put on its M3 chip? Its M3 Max has 92 billion transistor equivalents on that one chip in a currently shipping MacBook Pro. And what's going to happen with this in the future? Is it going to continue to double? Well, a lot of people think so. You know who thinks so? Intel thinks so. If you go to the Intel website, they will tell you that Moore's law is continuing unabated, and they believe that by 2030, with the continuation of Moore's law, Intel will be able to fit 1 trillion transistor equivalents onto a single chip. Think of how small those transistor equivalents might be. Well, this interesting development of transistor chip technology led a lot of people to think that maybe it wasn't just computer chips. In particular, this guy, a friend of mine named Ray Kurzweil. And Ray said, wow, Moore's law seems to apply to technology in general, but it really only specifically relates to transistor equivalents on a chip. How about if we generalize the description and say, instead of transistors on a chip, let's say instructions, computer instructions. How many capable instructions is it capable of doing? Let's say millions of instructions per second per dollar. Well, that's a whole big mouthful, but that basically ties together price and power and speed into one thing. So if you look at millions of instructions per second per dollar, you can apply that to any form of computing or calculation, including in theory an abacus. And if you take a look at the computing technology, he went back to the beginning of the 20th century. And you know what he found? He found that Moore's law effectively was operating from 1900. From when Herman Hollerith invented punch cards and founded IBM to create the things for the 1910 census, all the way through major paradigm shifts that changed the nature of computing and of technology, from relays and vacuum tubes to transistors to integrated circuits. It turns out that technology across the board has been advancing since the beginning of the 20th century at the rate of Moore's law, doubling every 18 months to 2 years. So then Ray said, well, wait a minute, if it could go back to the beginning of the 20th century with these major paradigm shifts happening at predictable intervals, maybe it's not just limited to the 20th century. Maybe we could take it back before that. And so he went and he collated everybody's assessment of all of the technological changes, the paradigm shifts, whether it was fire or the invention of the wheel or the Iron Age or tools or the Industrial Revolution, things like that. And he plotted on a graph to see how fast these paradigm shifts came into play. What do you think he found? Oh, it turns out that the equivalent of Moore's law, of this exponential growth in technology, has been going back since the beginning of recorded history. It has been developing at the same speed that it is developing at today. So now you say, how is that possible? Why didn't cavemen have iPhones? And the answer is that as people, we tend to think, we are trained as humans to think linearly. And that means we think about things in a straight line, either things staying together in a straight line or else moving at a trajectory that is a straight line. So for example, take a staircase or take a graph in which you go one step forward and one step up. Well, if you do that linearly, you go one step forward, one step up, 2 steps forward, 2 steps up. Every step forward you take, you go one step up. So therefore, if you go 30 steps forward, you are 30 steps up. But we are not attuned as people to think exponentially, because what happens there is you go one step forward, one step up. But the next step, you double it. Well, it's still the same 2 as you have linearly, but it's actually doubling because the next one is 4, and then 8, 16, 32, 64, 128, 256, 5, 12, and so on and so forth. So you know what happens if you take 30 steps forward exponentially? Well, you go from 1 to 1 billion in that same 30 steps. So if out of this entire talk today, there is only one word you know, I'm going to give you the one word that you should emblazon on your forehead and think about when you go forth from this metaverse session. And let's harken back, for example, to a great film, one of my favorite films called The Graduate. And there was this unforgettable line in there.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
So back in the day, the word was plastics. But today, the word for you to fix in your mind and think about morning, noon, and night, and you'll see why, is exponentials. And that is this doubling, inexorable doubling every single day, every single minute, doubling at a rate of every 18 months to 2 years. So what does that mean? That means the little computer you had, the computer that took us to the moon, has been outmoded. What is the current state of the art? It would take the entire population of the Earth more than 4 years to solve what this supercomputer, today's state-of-the-art supercomputer, can do in 1 second. And you know what? If you think that's where things are, that's the end of it, you better think again. Because just as powerful as that is, there's something even more powerful than exponentials. And that's when you start getting into quantum computing.
To confirm that our experiment was indeed hard to directly simulate, we benchmarked our quantum device against state-of-the-art algorithms on fast classical supercomputers. After a lot of careful analysis, we concluded that our demonstration went well beyond current simulation method. It's requiring hundreds of millions of years to recreate on the world's fastest supercomputer.
So that super faster cajillion supercomputer you saw would take hundreds of millions of years to do what the current quantum computers could do. And think of what that means in terms of this acceleration. But the interesting thing is it's not just getting more powerful. More things in our daily life. Everything is being influenced by technology, and it turns out that the percentage of the world that is attributable to information technology, to computers, is also itself growing exponentially. Who would have thought that hotel rentals, taxi cabs, all kinds of handcrafts are all tied into exponential growth? Well, they are. Because at the same time, not only is all of this power growing exponentially, not only is the ubiquity growing exponentially, but the cost is dropping exponentially, exactly as Gordon Moore had projected. And the reason this is important is this affects everything in our lives and things you might not even be aware of. We are all now so used to texting that it's second nature to us. But do you know that the first commercial text message was sent in 1992? At that point, back then, in the early 1993, I founded and ran the world's largest software developer that was doing text messaging software, which was great because there weren't that many of them, and you could do it from your computer sort of pretty easily. But if the first message was sent in December of 1992, today, in 2023, the number of text messages that are sent each day is twice the population of the planet. So all of this power and all of this growth is happening exponentially. Think about how it affects everything in your life. So for example, today, there are over 90 billion searches performed on Google each month. 90 billion, big number. Here's something for you to think about. Where did those 90 billion questions get answered before Google? If you think about the store of knowledge we have as a society, Many of you may remember that your parents or grandparents had this thing called an encyclopedia. The latest version of the Encyclopedia Britannica, the world standard thing, has 410,000 articles. But you know what? They stopped production of the physical books of the Britannica, even though it was the greatest encyclopedia ever done. And you know why? Because there's a bigger encyclopedia, and it's called Wikipedia. And Wikipedia has over 6,700,000 articles just in English. There is no way that any one person could have done that, any one company could have done that, any one team of editors could have done that. The reason they could have so many articles reviewed by lots of people working together is because this is what is known as an open source project, where people from all over the world without pay can come on and contribute to the growth of knowledge by writing and reviewing and editing these articles. And Wikipedia isn't the only open source project around. Take a guess in your back of your head as to how many open source projects there are, whether knowledge projects like Wikipedia, genealogical research projects, or software development projects. The answer may surprise you. Today there are over 3.3 million open source projects that are in play. And because so many of them have to do with software development, it turns out that 96% of all current software code contains open source code. And not just a little bit of it. 76% of the code that is currently in use is open source code. Think about what that means for the development and promulgation of technology. Here are some interesting numbers that might surprise you. The current population of the globe is about 8 billion people, plus or minus, right? 5.44 billion of those 8 billion people have mobile phones. That's 68% penetration of reaching every single individual person on the planet. 5.16 billion of those, or 64%, are using the internet, are all connected together. Just think of that, 64%, nearly 2/3 of the entire population of the globe is connected together over the internet. And when this first started, it didn't start that long ago. When I had my first computer connected to the internet, it looked like this, a little TRS-80 computer. And those things, for those who don't know, are called acoustic couplers. You put them over your telephone so that your computer could talk to the computers somewhere else, another person's computer. They didn't talk very fast. They actually talked at a rate of 300 bits per second. And so it may be hard to imagine for people who are used to multi-gigabit internet today, but this is what it looked like back in the day when you had a 300 BPS communication link. That's how fast it went. It wasn't graphics. It was just plain text on a plain screen. Compare that to today, not that long past the origination of this stuff. And today, the fastest fiber optic cables can transmit over 1 petabit per second. You have any idea how big a petabit is per second? To put that in perspective, that's the equivalent of 10 million 8K video feeds that are happening simultaneously. So we're creating all of this content, we're delivering all this content at speed, which means we can promulgate this and get people using this stuff faster and faster and faster than ever. Let's, for example, take a look at how many years it took to get to a market audience of 50 million people. Right, so if you start out with radio, it took radio 38 years to get there, but television only 13 years to get there. By the time the internet came into play, it only took 4 years to get to 50 million people. Facebook, 3 years. Twitter, 2 years. WeChat, 1 year. ChatGPT, which you're all probably using, 30 days. It took ChatGPT 30 days, less than 1 year ago today, to get to 50 million users. And today, currently, as we speak, ChatGPT is logging 2 billion visits per month. And what is ChatGPT? I assume if you're here in the metaverse, you know what it is. But it might be instructive to think about the latest version, which is ChatGPT 4, and see what they can do.
GPT-4 is the latest AI system from OpenAI, the lab that created DALL-E and ChatGPT. GPT-4 is a breakthrough in problem-solving capabilities. For example, you can ask it how you would clean the inside of a tank filled with piranhas, and it'll give you something useful. It can also read, analyze, or generate up to 25,000 words of text. It can write code in all major programming languages. And it understands images as input and can reason with them in sophisticated ways.
Now, this is not general artificial intelligence, the same thing that a human can, but for the kinds of things that we humans use intelligence for daily, it can come pretty close. Here are some stats you might find interesting about GPT-4. Not only can it do it in English, it can do it in 26 different languages. It passed the bar exam in the top 10% of people out there. It was at the top of the US Bio Olympiad, the top of the SATs, scored 5 out of 5 on a dozen of the AP exams over here. And that's just one example of artificial intelligence. Later this year, about 6 months after GPT-4, ChatGPT came out, Adobe introduced an equally earth-shattering example of artificial intelligence. Adobe, of course, is the dominant player of graphic design software. And their new ChatGPT and the generative artificial intelligence that we know about, including this graphic stuff, came out less than a year ago. Adobe less than 6 months ago. And if you think this is the state of the art and it's going to stop here, no, it's not.
It's called DragGAN. It's a new AI model developed by a bunch of these well-known companies like Google, MIT. It can take any 2 points in the image and drag it to another point and then generate the equivalent frame in real time. You can edit a 2D picture as if it's a 3D picture. Like you can make someone smile, you can change the perspective, you can change the dimensions of an object. It's ridiculous. Just take a look at some of these examples. I mean, look how crazy that is. This model is capable of analyzing your current point and making it meet that new destination point and changing the image in real time. So it's both image manipulation and point tracking at the same time. And look how natural it is. Now yeah, I get it, this is a demo, but still, it's a demo of a working model.
That's what's on the drawing boards right now, and probably is actually live today in general use. But it's not just being able to manipulate images, it's being able to manipulate artificially intelligent things like voice. So for example, here is my friend Salim Ismail, with whom he and I are doing an exponential executive program in the coming months, giving a speech about Moore's Law and the development of technology.
Doubling pattern is now occurring in a dozen technologies. En día, este patrón de duplicación lineal a exponencial es que mientras hemos visto la ley de Moore y este paradigma basado en la información durante 60 años, ahora ocurre en una docena de tecnologías. Es ist, dass wir dieses lineare bis exponentielle Verdopplungsmuster inzwischen in einem Dutzend Technologien sehen, während wir Moores Law und dieses informationsbasierte Paradigma seit 60 Jahren beobachten. So the reason this is so fundamental today, this linear to exponential doubling pattern, mientras hemos visto la ley de Moore y este paradigma basado en la información durante 60 años, paradigma seit 60 Jahren beobachten.
This AI took his voice, created a voice clone, translated his speech into another language, played that speech back in his new artificial language, and matched it to his mouth movements. That's the kind of thing that you can do live today. Think about where this is going. Think about all of the patents that are currently being issued. This gives you an idea for frontier technologies of how many fundamental patents are being granted in the US. They are not just patents of machines, of things, or of crops. We're now talking about fundamental technologies, digital technologies, physical technologies, biological technologies. The percentage of patents that were about artificial intelligence is up 718%, big data 700%. All of these areas are being developed at breakneck speeds, not just in the US, but around the world. And all of these are leading into what many of you have heard of as something called Web 3.0. If Web 1.0 was brochureware and Web 2.0 was an interconnected web of things, Web 3.0 combines a whole lot of really interesting frontier technologies into one cohesive whole. Whether you're talking about 3D graphics, about connectivity of everybody everywhere at high speed, of the ability to have decentralized teams and peoples and resources and information and data and computing power, whether you're talking about digital identities, whether visual or graphic or actual personal identities that can travel with you around the web, the ability to monetize this through micropayments and cryptographic technologies and funds, cryptocurrencies and the like. Whether you're talking about AI and big data, everything we do is now being monitored and being analyzed through machine learning and put into artificial intelligence, being connected with each other on the blockchain, not requiring intermediaries, but a trustless state of the universe, of semantic web, which can actually take all this data and put it into some kind of rational form. And all of this is leading up together to one place where this exists. And where is that? Well, that's the metaverse. And that's why we're all here today to discuss where the metaverse is going. So you might ask, what's the first question? What the hell is the metaverse? And one way to think of it, if you want to have a whole mouthful, is that the metaverse can think of it as a digital landscape of decentralized, hyper-connected, virtual reality environments that embody the internet for socialization and work. Try and say that 3 times fast. But what we're basically saying is all of those technologies, all of these things are coming together in one cohesive whole that can work with people to give you visual and spatial representations of all of that data and power and connectivity. So the metaverse is based on 3 sort of fundamental sets of technologies. One of them is blockchain, which has the ability to connect data and systems across the world, all kinds of things without any central intermediary, but all working on a universally trusted, trustless operation. You then have artificial intelligence, which is built on this, which today already amazing things. Everything there was generated by AI, artificial intelligence. And the next major thing is not only generative art, is not only connectivity with the blockchain, but then integration into our lived experience. The most eagerly anticipated of these new steps into the metaverse is Apple with the Vision Pro, coming out this year.
Your favorite apps from Apple and the App Store are there. You can arrange them however you like and work seamlessly across them.
Hi. Hey.
Hi, did you receive the deck?
Yeah, I'm looking at it now. Oh, great.
So what did you think?
FaceTime looks and sounds amazing in Apple Vision Pro. You see people life-size, and with spatial audio, you hear them as if they're right in front of you. So conversation is more natural, and collaborating becomes even easier. And because you see the world around you, you can glance at a notification and even connect your Mac simply by looking at it, turning a 13-inch screen into a giant display. In Apple Vision Pro, you can also transform your space. Beautiful environments let you extend beyond the dimensions of your room.
So what happens when all of these technologies come together? All of these things that are pushing the frontiers of what we know, what we think computers and people are capable of doing. What happens when you combine the awesome computing power of Moore's law directly applied to chips when you tie that into autonomous transportation, whether it is now self-driving taxi cabs that are on the street in San Francisco, self-driving submarines, self-driving planes, which are already being tested out there. You take a look at manufacturing and production robotics. Everything you're looking at and using these days is being built by a person. The extraordinary power of ChatGPT and equivalent generative AI. Already there are other AI platforms, fundamental foundational large language models from Anthropic and open source models that Meta is working on, where you have the ability to do things you would be unheard of previously. For example, in terms of the man-machine interface, human interface over there, what you're looking at here are brainwave images. The things at top are images that people were looking at, and the things beneath them are the reconstructed images that brain sensors outside your brain could do. Computers today can see what you are thinking. And it's a very small link from there to be able to go the other direction and create it. Neuralink, which is Elon Musk's new company, has gotten FDA approval to do live patient implants. Imagine when you're not going to need to have an Apple Vision Pro to be in cyberspace, in the universe there. And meanwhile, at a microscopic level, nanotechnology is letting us create entire factories and robots and things in your blood. Imagine little robots that are going in and killing cancer cells in your blood. And you have large-sized robots, too. These robots from Boston Dynamics, if you've ever seen some of their demos, are mind-blowing. Atlas and Spot. These act like people and dogs, and they can run farther, jump faster, and do everything physically almost better than you can doing it over there. And we haven't even talked about one of my most fascinating areas that I'm really interested in, and that is the idea of swarm robotics, swarm intelligence. If you take thousands and thousands of teeny little things that are special purpose, single little robots, whether they are drones or robots on legs or on wheels, and they come together and they can each of them do something that the whole group couldn't do if it was programmed by a single central intelligence. And so when all of these things come together, in the same way that ChatGPT was trained to figure out what would a human say in response to certain input, it wasn't trained to program. Except now, you know what? ChatGPT can program as well as many computer programmers. And that kind of behavior is known as emergent behavior. It's something we didn't program, but is coming at us and is being generated by technology. So where does all this lead, and why is all this important now? This all leads to something that Ray Kurzweil has been the primary champion of, but that caused us to found Singularity University, of which I'm an associate founder, and I founded the finance, entrepreneurship, economics track there. The technological singularity is that point in time at which humans and computers effectively merge. It's the next paradigm shift. And when computers and humans merge, and the next generation of computers is designing the following generation of computers, with or without human help, the potential changes for our civilization, whether for amazing good or horrific bad, are absolutely unimaginable. You cannot foresee what they are going to be. That's why we call this the event horizon. And, when is this going to happen? Well, let's say we're only, 1% of the way there in, 15 years, right? Say 15 years from now, we're 1% of the way there. What does that mean? Well, given exponentials, remember that word that I told you never to forget? That means, according to Ray Kurzweil's predictions, which have held up remarkably well so far, the technological singularity is going to occur when? In 2045. We're now entering 2024. So therefore, within 21 years, we are going to potentially be at this incredible place of the technological singularity beyond our ability to even imagine that. And you know where all of that is going to take place? It's going to take place in the Metaverse. And that's why I'm delighted to welcome you to the Metaverse Spectrum Business Conference and Expo. Have a wonderful 2 days. Thank you.